All right, Unit 6, progress check, FRQ number 3. So we've got a cylinder that's connected to a spring, and the spring is connected to the wall, and they're connected by a string that wraps around the cylinder. And there's the side view right there. It says a group of students would like to determine the spring constant K of the spring. So we're solving for K. As shown in figure 1, one end of the spring is attached to a wall and the other end of the spring is attached to a string. The string is wrapped around a horizontal cylinder of known rotational inertia IC. Okay, so that's a known value, a known quantity. The cylinder can rotate about a fixed horizontal axle with negligible friction. So we don't have to worry about any torque on our cylinder as it rotates due to friction. Describe an experimental procedure to collect data that uses the setup shown in figure 1 and also would allow the students to determine K by making a linear graph. In your description, include measurements to be made along with the corresponding equipment needed for each measurement. The students do not have access to any devices that can measure force or mass. Provide enough detail so the experiment could be replicated, including any steps necessary to reduce experimental uncertainty. I'm going to focus on the guiding concepts in the problem as to help you start with a derivation. So I'm going to redraw the image and talk about the free body diagram here. So we've got our spring like this, and there's a string, and then it wraps around a cylinder, and that cylinder is connected to an axle and rotate. And I'm going to say that my system is the spring plus the cylinder. Let's talk about why. When I see this problem, I see energy transferring from the spring to the cylinder and vice versa. So, for instance, if I wind the wheel in this direction, the clockwise direction, as seen from this angle, the string will want to move this way, and that'll extend the spring and give the spring energy. If I then let go, then the spring will move back in the other direction, right? And that will cause the wheel to unwind. So, there's just as the spring loses energy, the wheel will gain energy. Now, I want to stop and talk for a second about the forces. Are there any net external forces on the system doing any work? All right. In terms of the reason why I'm talking about work is because I'm concerned with energy. I've got energy of the spring, which is potential energy of the spring, not UG, sorry about that, US. And then I've got kinetic rotational energy of the cylinder. But is there any work being done on the system? Well, we're concerned about external forces. We could throw the string in there as well. All right. And even though the string is not, it's not declared as massless, if you look at it, it's very tiny in comparison to the cylinder. So, even though it doesn't say it's massless, I'm going to assume it's a quote unquote massless spring. It wouldn't affect the experiment too much. So what is going on? We've got a force of the wall right here. Let's say I actually wind up the cylinder by rotating it clockwise, which will then extend my spring a little further. So maybe in red, I'll show the spring further along. So now I've displaced the spring this much, and that's going to cause the spring to want to go this direction, which means that the wall must be supplying a force in this direction. So I'm going to write F wall. Okay. Now the axle, right, must be pulling the other direction. How do I know that? Well, if it wasn't, then the whole system would move to the left if we only had the force of the wall. So those forces must be equal in magnitude in opposite direction, so the net force on my system is 0. And if that's true, right, if the net force is 0, then the net work being done on the system is 0 as well, okay? Even if you look, at the work being done by the wall F parallel D, right, the wall is not moving anything, so really your displacement value is 0. You could say that the center of mass of the spring moves a little bit, but again, it's pretty much a massless spring. If you look at the work done by the axle, again, F parallel D, right, there is no displacement of the cylinder. So again, your D value is 0. So we have no work being done. So what does that mean? That means that we don't have a net external force doing a quantity of net external work on our system. So energy is conserved. So if that's true, right, our guiding equation is initial energy plus work equals final energy, but the work being done is 0. Well, what kind of initial energy do we have? Well, if we wind up the cylinder, right, then we have rotational kinetic energy. And if we let go, all that energy is going to transfer to the spring. Oh, I'm so sorry. I messed up. If we wind up the cylinder, the spring is stretched. So we'll have let's go step by step. We'll have spring energy, US. And if we let go, right, the wheel will start to turn and we'll have rotational kinetic energy of the wheel. So it's just a transfer of energy from one object to the other. So now let's replace US with 1/2 K x squared, where x represents the displacement of the spring, right? In this picture right here, this is x, the stretch from its natural length position. And then rotational kinetic energy, 1/2 I omega squared. All right. Now, it did say we're solving for K, and we know I is a given value. It's IC. So we can replace I with IC because specifically that's the known quantity of the moment inertia of the wheel. And the question is asking, how can you create a linear graph that would help us find K? Well, what we need is something in the form of y equals mx plus b. Well, we don't see any plus signs in our equation, so it's probably just going to be y equals mx, right? We're probably not even going to have that. So then we have to say, what can we graph on the y-axis, and what can we graph on the x-axis? Now, we need to create a linear graph, so we need to be careful because it might be logical to say, oh, the angular rotation, the final angular rotation of the cylinder is going to depend on how much we stretch the spring. But if you actually rearrange the equation for omega, right, what would we get? Let's go solve for omega. So multiply each side by 2, and then I'll do some work over here. We have kx squared equals IC omega squared. So I'm going to flip things. I'm going to write omega squared equals kx squared over I, right? So, and then if you actually solve for omega, you have to take the square root of each side, and you get the square root of k over I times x. Or showing it in steps, sorry. Let's show the math there all the way. So you would say, let's just show the math. So square root of each side, and you get omega equals, now when you see everything underneath the square root sign is just multiplication and division, you can break it into parts. So I would break out k over I, because those are constants, times the square root of x squared. And this would simplify to omega equals the square root of k over I times x. Now, oh, well, look at that. We could do that. Check this out. So if we plot omega on the y-axis, and we plot displacement of the spring on the x-axis, this value right here gets multiplied by our x variable, so that would be m. So that works out pretty well. So in other words, we would expect to see a linear graph if we did omega as a function of x. That's what this derivation shows us. And if we find the slope, right? Well, by the way, I want to point out that 0, 0 does make sense, because if you don't stretch the spring at all, you wouldn't expect the cylinder to rotate. All right. And then from 0, 0, we would expect some sort of linear graph, and we do a best fit line, and the slope of this line, right, we could set equal to the square root of k over I. Right? And then you could mathematically solve for I. So the next step then would be to take whatever that slope value is and solve for I. So if I say m equals the square root of k over I, and now I'm solving for k, my first step would be to square each side of the equation. And then I get m squared equals k over I, well, sorry, IC, and then multiply each side by IC. Right? And then you get, I'm going to flip it, k equals IC times m squared. So whatever the slope turns out to be, you'd end up just having to square it, then multiply by IC, and then that would give you k.